Good evening. My name's Scott Tremaine. I'm Richard Black, Professor of Astrophysics at the Institute. I'm very pleased to introduce Eli Waxman. Eli got his PhD from the Hebrew University and was a member here from 1994 to 1998. After that, he moved to the Weizmann Institute, where he's now professor in the departments of astrophysics and particle physics. He's made a wide range of contributions, research contributions, specializing in events the highest energies in astrophysics and in transient and explosive events. He's made major contributions to our understanding of cosmic rays, very high energy neutrinos, gamma ray bursts, supernovae, and many other subjects. He is currently the Israeli principal investigator for the first Israeli astronomical satellite, which is to be a joint project between the Israel Space Agency and the Jet Propulsion Laboratory, and is to look for transient events in the universe. In the past 3 years, he's been on leave of absence from the Weizmann Institute, working on research and development in the Prime Minister's office. The bad thing about that is that we try to get him to come here every year, and he hasn't been able to come as regularly. The good thing is that it's given him special insights into the subject of this evening's talk, which is a physicist's perspective on the Iran nuclear deal.
Thanks, Scott, for this introduction. In the coming hour or so, we will be discussing the Joint Comprehensive Plan of Action, which is the agreement signed by Iran and the P5+1 group of world powers. This is the US, Russia, China, the UK, France, and Germany. The agreement is aimed at limiting the Iranian nuclear program with the goal of preventing or reducing the risk of it achieving a nuclear weapon. I will try to explain the logic of the agreement, the content of the agreement, and to discuss the effectiveness of it towards achieving this goal. I will not be discussing the agreement in terms of is it good or bad. And this is for two main reasons. First, I don't want to get into more trouble than I'm already in. And second, which is maybe more important, I think it's not the right question to ask. So the real question that we need to ask ourselves is what the alternatives that are available, and what are the advantages and risks associated with these different alternatives, and then form an opinion about the suitability of the agreement. I will try to give you some tools in this talk to form an informed opinion about the advantages and disadvantages, and therefore make your own judgment. I will devote much of the discussion to introduction, because this is crucial for understanding the agreement. The first topic that we will discuss is what is a nuclear weapon? We will then ask what infrastructure is required in order to produce such a weapon. We will then be ready to ask how far did Iran get? And how does the agreement, the Joint Comprehensive Plan of Action, change this situation? And finally, I would say just a few words about verification and about alternatives. Now, I would encourage you to ask questions during the talk so that I get the feeling that someone is listening. And I guess we would not be running with the microphones, but I will repeat the question that will be asked during the talk. We start then with nuclear weapons. I assume that you all know that the matter that we are made of is composed of atoms, and that these atoms are composed of nuclei, positively charged nuclei, surrounded by negatively charged electrons. We will mainly be interested today in the nuclei. And the nuclei themselves are composed of two types of nucleons, the neutron and the proton. The neutral neutron and the charged, positively charged proton. The lightest atom, the hydrogen, the nucleus of the hydrogen is simply a single proton. The next lightest nucleus is helium. And the helium nucleus is composed of 2 neutrons and 2 protons. So each nucleus is defined by 2 numbers. The total number of nucleons in the nucleus, so this is 4 for helium, 1 for hydrogen. And the number of protons in the nucleus, which is 2 here and 1 here. For a given number of protons, there could be several numbers of neutrons in the nucleus. Since the chemical properties are determined by the number of protons, by the electric charge, so several nuclei with the same number of protons but differing number of neutrons will behave similarly chemically, so they are called the same name, the same material. But we could have, for example, hydrogen with 1 proton and 1 neutron. Okay, so this is H with 2, 1, and this is usually called deuterium. And different numbers of neutrons with the same number of protons are called different isotopes of the same type of material. Okay? Now, the energy source of the sun is burning hydrogen into helium, nuclear burning, combining 4 nuclei of hydrogen into 1 nucleus of helium. This releases energy, and this is the energy source that supports the sun against its own gravity and produces the sun's luminosity, which keeps us alive. Okay? Now, once the star converts all its burnable hydrogen into helium, stars heavier than the sun continue to burn the nuclear fuel to even heavier elements. So most notably carbon, nitrogen, and oxygen. Okay, so this 6, 7, 8, 12, 14, 16. Okay. Once carbon, nitrogen, and oxygen are burned, you form heavier elements, and this ends when the star converts its nuclear fuel to iron. Iron is the sort of most stable nucleus, and you cannot gain more energy by adding nucleons to the iron, so the star has consumed its energy source. What happens then, Adam will excuse me, is not entirely clear, but some process occurs and the star explodes as a supernova. In a supernova explosion, heavier elements are produced, and we will be mainly interested today in uranium and plutonium. Okay, 2 quite heavy elements with about 240 nucleons in the nucleus. If we plot the energy that we obtain by combining nucleons into nuclei. So this is the energy per nucleon that we obtain as we increase the number of nucleons. The graph would look something like this. Okay. Some dip here, which is not so important for us. So here is hydrogen with no gained energy. There's deuterium, helium. Here at the top we have the iron. And here somewhere up we have uranium and plutonium. So we can gain energy in two ways. One, by combining light nuclei into heavy ones. So this is called fusion. And the other is by breaking up heavier nuclei towards the iron. In each of these directions, we gain energy. This is called fission. Okay. The units of energy, this is usually measured in what we call mega electron volts per nucleon. An electron volt is a microscopic unit of energy. And to give you some calibration of how much energy we are talking about, we can compare it to chemical reactions. Okay? So chemical reaction like eating chocolate. Okay? And you eat chocolate, you get roughly 1 electron volt per 10 nucleons. And if you convert it to units, I guess most of you are more used to, this would be 1 calorie per gram. Okay? This is the same for eating chocolate and for exploding TNT. No difference, roughly. Actually, chocolate has more energy than TNT. The difference is that TNT burns very, very fast, produces an explosion. And chocolate accumulates over many years and has different effects. Right. Now, you see that the factor here is 10 million. Okay? So this is larger by 10 million. Which implies that if we take 1 kilogram of nuclear fuel and we burn it, we get the equivalent of 10 million kilograms of TNT. So 10 million kilograms of TNT, which is usually called 10 kiloton of TNT. Okay, 10 million. So the amount of energy that is released is enormous. Now, how can this energy be utilized? Today, we will talk only about this direction of fission. This is the simplest nuclear weapon based on breaking up heavy nuclei towards light ones. Okay? And most heavy nuclei can be broken up by firing a neutron into them. So you fire a neutron into a heavy nucleus, and it breaks up to 2 lighter nuclei and releases energy. Now, in order to get an explosion, we want this reaction to just carry on by itself. Like you ignite the TNT and it just burns up and explodes. In order for this reaction to continue by itself, we need that in this breakup, in addition to the production of the 2 lighter nuclei, a few new neutrons will be generated. In this case, these new neutrons would meet other heavy nuclei, like suppose that these are the heavies, and they would cause them to break, they would produce more neutrons, and so on, and this process would explode. Okay? Materials that have this property are called fissile. And you can imagine that I didn't mention these two just by chance, because these are the 2 fissile materials that we are going to talk about, the uranium-235 and the plutonium-94. Okay. Now, I will just wipe a little bit here. In order for this reaction to take place, we need to have a sufficient mass of the fissile material, because if we think of, suppose we take a very small sphere of mass, then many of these neutrons would just be escaping outside. So this reaction will not continue. The neutrons just escape. If, on the other hand, we take a large mass, then all the neutrons would be stuck, and we would get an explosion. Okay? And there's some particular mass in which, suppose that we produce 3 neutrons every time, 2 neutrons escape, and 1 neutron remains in the system. In this situation, the reaction will just maintain itself and not explode. So this is called the critical mass. Okay, so this is small m, this is large m, this is just the critical mass. For the 2 elements that we've discussed, for this uranium-235, we need roughly 50 kilograms. And for the plutonium-239, we need roughly 15 kilograms for the critical mass. Now, suppose that you have this critical mass. How do you build a bomb out of it? If you take some piece of matter with more than the critical mass, it would just explode, because there are neutrons all around here all the time, and there are also some spontaneous fission in the uranium or plutonium that would lead to the explosion. So, of course, the idea is to either, there are 2 basic types of such weapons. One is based on the idea of taking 2 subcritical masses and then shooting one of them onto the other. And when the 2 meet, they exceed the critical mass and can explode. So this is sort of called a gun type device. Okay? And the other type of device is an implosion device. So you take some mass which is smaller than the critical mass, and you surround it by some explosive, say TNT. And when you explode this TNT, it compresses the fissile material here. Now, the critical mass decreases when the density of the fissile material increases, because for a denser material, it's more difficult for the neutrons to escape. Okay? So then after you explode it, you can get a nuclear explosion. Okay? So in order to prepare a nuclear device, we need 2 things. We need some mass of fissile material. And it's going to be a bit smaller than these masses, because in this case, we are using less than the critical mass at normal density. So we need something like 30 kilograms of uranium-235 and something like 10 kilograms of plutonium-239. The second thing that we need is an explosive device. Some device like this that would make the fissile material into a bomb. Now, I would make one distinction here. I'm writing an explosive device and not an explosive weapon. It is more difficult to produce a weapon, which is a device that you can put on a plane or a missile. Okay, you can build a much larger, less robust device in your laboratory that cannot be carried by a missile. The point is that if Iran achieves a nuclear device and explodes it, it has done 99% of the way. So what we want to prevent is not a nuclear weapon, but rather a nuclear device. And this is a more stringent requirement, okay? But this difference is important, and therefore I will write here device. Okay. Now you all know how to build nuclear weapons, so we can move to the next topic. Okay, good. So what do we need then? We need two things: the fissile material and the explosive device. So what is the problem? Let's start with the uranium. Uranium can be extracted from rocks. The problem is that most of the uranium that you find is not of this isotope with 235 nucleons, but rather with 238 nucleons. This isotope constitutes 0.3% of the nuclei that you would find in a mine. So only 0.7% is of the fissile type that you need for producing the explosion. Now, why is that, by the way? So this is because these heavy nuclei are not stable, right? They are beyond this best mass, so they decay. They disintegrate spontaneously. The lifetime of the 238 is 4.5 giga years. So if you take a piece of this uranium and wait for 4.5 billion years, half of it would decay to lighter nuclei. On the other hand, the 235 has a shorter lifetime of 0.7 giga years. Now, the age of the Earth is about 4.5 giga years. And we know this, by the way, by looking at the decay chains of these elements. Okay, this is how we determine the age. So this supernova that occurred 4.5 giga years ago and led to the creation of the solar system and so on, produced some uranium, plutonium, all this stuff. But most of the 238 have decayed, 35 have decayed by now. Okay? Now you see that we live in a difficult time, right? Because if we wait a few more giga years, all these 235 would disappear, and we would have no problems with Iran. But this is not a practical solution, okay? So we need to do something else. Okay, so the first challenge then is to extract this fissile uranium from the 238 majority. Now, because the chemical properties of the two are the same, and because the masses are very close, it's very difficult to separate the two, because they behave almost the same in every process that you try to apply. And the most efficient way to separate them is to use centrifuges. So a centrifuge is a cylinder that rotates very fast, typically a meter high, 10 centimeters in diameter, rotating at 1,000 revolutions per second. Okay, and this is the challenge. When you put gas into such a centrifuge, the heavier elements are pushed more strongly outside because of the centrifugal force. The lighter ones remain more close to the center, so you can separate the two masses. So typically, you put in something at 0.7% 235, and you take out something, let's say, at 0.9 at the top, and remove something at 0.5 at the bottom. Yes?
How do you convert the rock element to gas?
Okay, so the question was how the rock element is converted to a gas. So first I would say that the gas that is fed to the centrifuge is UF6. You've probably heard of this, uranium hexafluoride. The property of this material is that it sublimates at relatively low temperature, 55 degrees centigrade. Don't ask me about Fahrenheit, but it's sufficiently low. And so there is a process, there is a set of processes taking the uranium oxides, typically U3O8, from the mine and converting them to UF6. I will not discuss this in detail because we do not have time. But this is a well-known, rather simple process. It's not the challenge of the... Okay, now you see that we've only increased from 0.7 to 0.9. To get to something that would allow us to build a nuclear weapon, we need to get to 90%. Okay? So in order to get to 90%, you need many stages. So the idea is that you take many of these centrifuges, you feed these with the 0.7%, they go up to 0.9. Here there's another set of centrifuges that get this 0.9 and get up to higher fractions and so on. So such a configuration of centrifuges, okay, that you put 0.7 here and you get something like 90% out, is called a cascade of centrifuges. And without going into too much detail, I will just tell you how many centrifuges and how much time it takes to start from natural uranium to get to 90%. So for the type of centrifuges that the Iranians have built, they are so-called IR1s, you need 600 centrifuges working for about a year to produce these 30 kilograms of enriched uranium. Okay? So for the infrastructure, we need 6,000 IR1 centrifuges times 1 year to get to the 30 kilograms of fissile material. And once you get this material, you get it in the form of enriched UF6. You need to have some process that would convert it into a metal piece of uranium that you can use for a device. So you need some UF6 to U metal conversion facility. Okay. So this was about uranium enrichment. Is it okay? Understood? Okay, very good. Okay, it goes too fast. You would start building your own devices soon. What about plutonium? So plutonium-239 the lifetime of this element is some 20,000 years. So this is very short compared to those ages, which means that you don't find it in nature. Okay? You have to produce it artificially. And the way to produce it is to irradiate this uranium with neutrons. So you take uranium-238, you add a neutron to it, it becomes uranium-239. And this uranium-239 decays in 2 stages, 2 beta decays to plutonium-239. Okay? It converts 2 of the neutrons to protons, becomes plutonium. How do you take a big mass of uranium-238 and irradiate it to produce plutonium? This you do in a nuclear reactor. What is a nuclear reactor? Very simple. It's some large vessel where you have, simplifying it, uranium rods surrounded by water. Okay? Now what happens is that a neutron that is produced by some fission of uranium-235 in this rod, the neutron would normally escape. These rods are typically 1 centimeter in diameter and so on. So the neutron escapes. So without the water, nothing would happen. This would be a subcritical system. Now what water does, as the neutron escapes into the water, it starts scattering here and eventually gets back into the uranium fuel and produces another fission. So the water acts not only as a reflector, but also as the neutron scatters here, it slows down. And when it slows down, the cross-section, or the probability that it would be able to break up the next uranium nucleus is higher. Okay? So this is an exactly critical system. Okay? You maintain it such that the number of neutrons doesn't increase and doesn't decrease, okay, unless you have an accident. And in this process, you produce plutonium. Now, it is much more efficient to produce plutonium in heavy water reactors. You replace this hydrogen with the isotope deuterium that we had there. And the reason is the following. If you use just regular water, okay, and you use natural uranium, you cannot get criticality. You need to enrich the uranium a bit, typically to 3.5%, in order to reach criticality. Now, when you move to deuterium, you can use natural uranium. And the reason is that water, except for scattering, also occasionally absorbs one of those neutrons. So one of the hydrogen in the atoms in the water absorbs a neutron to become a deuterium. Now, when you use deuterium, heavy water, the deuterium has already its second neutron. It doesn't absorb so much. And therefore, you can live with a natural uranium, so that this is 0.7%. Now, the rate at which you produce plutonium is proportional to the fraction of uranium atoms which are of this type, of the 238. Okay? So here, you have 5 times larger fraction of this 238. So you get 5 times faster production of plutonium. And typically you get 1 kilogram of plutonium for 4 megawatts year of operation. So if you have a nuclear reactor that produces 4 megawatts and works for about a year, you get 1 kilogram of plutonium. Okay? So the second thing that we can use is a heavy water reactor using natural uranium. And if we want to produce material for a device, we need something like 40 megawatts, okay, to produce the fissile material that we need. Here, the conversion of the plutonium to some metal piece that you can use is more complicated. You have to take out the plutonium out of this irradiated fuel, which is very radioactive. So it's very, very difficult to handle. It's not a simple process. You need a complicated separation device. Okay. So now, are there questions about what's needed here?
Is that what they call a breeder reactor?
No, a breeder reactor, well, sort of. A breeder reactor in general, so yes, but not the most general form. A breeder reactor is a reactor that produces more nuclear fuel than it consumes, so it produces more fissile nuclei in its operation than it consumes. Right, so one type of new fuel that you can produce is the plutonium, but there are other types. Yes.
I was going to talk about the costs.
The cost?
For those. These are optional.
So, okay, we can talk about the costs later, yeah.
Can you explain the factor of 5 again? Because the factor of 5 is used in 35, right? I thought it was 38.
So, okay, I'll just write this for you, but if anyone, right, not only for you, but for some of the physicists here, but the rest can ignore it, okay? So the power of the reactor is proportional to the neutron flux times the number density of the 235, because this is what produces the fission. The plutonium production rate is proportional to phi times the number of 238, right? Now you divide the two, you get the factor. Okay. Actually, I'm cheating a bit, but it's okay. Okay. More questions about this part? Okay, good. It's the first time I'm using this sophisticated machinery. Okay, good. Now that we know what a nuclear device is, we know what the infrastructure that is required for its production is. We move next to asking, okay, how far did Iran get? So let's say before the agreement, what did Iran have in terms of uranium enrichment? So Iran built two large facilities for enriching uranium. One in a place called Natanz. Natanz is a big bunker with several meters of concrete on top. And it held 15,000 IR1 centrifuges, okay, and 1,000 centrifuges of more advanced design, which are called IR2. They are probably more efficient than this by a factor of 3. We don't exactly know. So this is a bunker. They also had another facility in a place called Fordow, which is a tunnel dug into a mountain, where they have 3,000 IR1s. In addition, they have started accumulating fissile material. They had some 7 tons at enrichment of 3.5% and some 300 kilograms at 20%. Okay. Now, if you ask what the implication of this is in terms of reaching these 30 kilograms, it means that upon decision, they could have reached 30 kilograms in a matter of few weeks. Okay. Next, I'll leave a place here for what happened after the agreement. Again? How many?
In a few weeks, 1.
3. Doesn't matter. 1, 3. Actually, there were big arguments about this, but it's not important, right? Okay. What did they have in terms of plutonium? Okay, they were building in Iraq, a nuclear reactor that the parameters of which you can guess. Okay. D2O, natural uranium, 40 megawatts. It's all consistent with a peaceful nuclear program. So that's what they were building this, but they were not, okay, they had no separation or infrastructure, or not the beginning for the construction of a separation plant. And I'll leave here someplace. Okay. What about the explosive device activity? So this is the activity for achieving the fissile material. What about the other route of constructing the explosive device? So here I will talk a little bit about the IAEA and so on. In 2002, the construction of this site and this site was exposed. So Iran did not declare it, and it was exposed by opposition organizations and the intelligence services. And following that, the International Atomic Energy Commission, which is a body, the main goal of which is to monitor the production and use of fissile material to make sure that it's being used for peaceful purposes, started an investigation. Okay? I will not go into all the details, but I will just tell you what were the results of this investigation. This part of this, yes?
Actually, I have a question about the plutonium separation. How difficult is it once you have this reactor to do the separation?
Okay, so we go back a little step, but it is quite difficult because the fuel is very highly radioactive. You cannot just handle it in a lab, right? And the chemical processes are complicated and corrosive. So it's a big feat. Yeah. Okay, so going back to this, the International Atomic Energy Commission started to investigate what is called the possible military dimensions of the Iranian program. This is something that you may have heard of, this acronym PMD, the possible military dimensions. And in short, what they have found, some highlights. They have found documents explaining how to convert the enriched UF6 to a metal sphere. Okay? They found that the Iranians have been developing the special type of detonators that are needed in order to produce this explosive device. So you may have heard of this. This is 1 microsecond explosive bridge wire detonators. Now, these are things that the Iranian admitted that they had. They did not even deny it. The IAEA also found many other things that the Iranians denied, like nuclear weapon calculations. Like workshops for missile integration. And the list goes on. I'll not detail it all. Maybe I'll mention one more thing that you probably have heard of. This hydro test in Parchin. So the Iranians have installed an explosion chamber. So this is a big cylinder which can hold an explosion of 70 kilograms of TNT, and which is normally used for testing the explosive part of the nuclear device. These things Iran denied. Okay? Now, when I say the IAEA found, means that some intelligence services provided it with information. They went to Iran, asked questions, and did not get the answer or got evidence for this activity. Now, based on this, and again, in spite of the fact that it looks all very peaceful, the IAEA declared that what they find in Iran is consistent with a program for developing nuclear weapons under a single organization, which is called the Ahmad Plan, okay? And that had a clear plan for doing this. Following these results, the United Nations Security Council started imposing sanctions on Iran from 2006 to 2009. And these sanctions were increasing. The economic sanctions were becoming tougher and tougher. And the Iranians, following this, went into negotiations with the world powers. In November of 2013, an interim agreement was signed between the P5+1 and Iran, the Joint Plan of Action, which halted the Iranian progress. So this stopped the Iranians at this point. Okay, once this was signed, they stopped making progress on the program. And this led to negotiations that finally were concluded with the final agreement, okay, for which they found a new original name, the Joint Comprehensive Plan of Action. This is the JCPOA. And it limits the Iranian program in a way that I will describe next. So far, so good? Yes?
UF6 to metal process, do you need that to create your 6% reactor or 3.5% reactor hub? Is that only applicable to your 90% high?
So in the reactor, you don't use metal, you use an oxide. So it's a bit different, but you are right that the border lines between those things are not so clear. Right? So this is another worry, yeah. Okay, what does the JCPOA achieve? Before that, I'll use a board here. So I would like first to talk about the logic of the JCPOA and then explain the details. So what is the logic of the JCPOA? We want to set limitations and constraints on some activity that Iran is carrying out in order to make it harder for them to make progress. Okay? So we want to limit some activity which is, first of all, critical to the process. If you don't have to do this for achieving a nuclear weapon, there's no point in restricting it. Second, we want to make sure that the limitations that are set are such that in the event that the Iranians decide to break all the rules, to throw out the inspectors, to do whatever they want, regardless of any agreements that they've signed, that it would take them a sufficiently minimal time to complete this activity. And what is a sufficiently long time? Some time that would allow the world to react. Okay? So this time is called the breakout time. So we want a minimal breakout time. This is not the supernova breakout, Adam. It's a different breakout. And finally, we want this activity to be easily identifiable. So we want to have high confidence of being able to identify the beginning of the activity should the Iranians decide to do it. Because if we are not confident that we will detect it, it doesn't help us that the breakout time is long, because we may detect it near the end or not at all. Okay? So we want this to be identifiable. Now, if we go back to this type of actions, you see that the activities on the weaponization side are not going to meet this criteria. The activities for the production of plutonium or uranium are large-scale industrial activities, okay? You need many people, you need big infrastructure. It's difficult to hide. These activities can be done in some laboratories, smaller number of people, it could be scattered. We will have low confidence that we will be able to detect it. So the agreement is focused on limiting the capability for reaching fissile material, okay? And to limit it in such a way that the breakout time would be larger than 1 year. This was the requirement that was set. So if we define the breakout time as the time it would take the Iranians from kicking off the program to reaching the sufficient quantity, the breakout time that they have been at was a few weeks. And the point was to extend it to a year. And in order to achieve this, the number of centrifuges in Natanz were reduced to 5,000 IR1s and 0 IR2, and in Fordo to 1,000 IR1, which are not allowed to process any nuclear material. So there are no nuclear materials allowed here in Fordo. And the reason, of course, is obvious. A tunnel is much more secure. It's much more difficult to bomb a tunnel than a bunker. Now, these quantities of huge quantities of materials, okay, with this number of centrifuges would still give them a very short breakout time. So they are limited to less than 300 kilograms of 3.5% and to 0 at 20%. Okay? This set of constraints gives this breakout time of about 1 year. Okay. What about the plutonium channel? So Iran was required to remove and destroy the calandria, this device that holds the nuclear rod fuel, and to rebuild a reactor. And this would be a different type of reactor. It would still be D2O, but it would be operating with 3.5%, and power would be limited to about 10 megawatts. So this would produce less than 1 kilogram of plutonium per year. Okay? So this sets the timescale for the plutonium channel to well above 1 year. Okay. I would say just a couple of words in a minute about this part of the agreement, but I would like to add some timelines here. So these restrictions on the centrifuges is for 10 years. And also for the nuclear material. From 10 years onwards, they can increase the scale of their enrichment program. Okay, so for 10 to 15 years, there could be a gradual increase in the enrichment capacity. There are some components which are restricted to 20 and 25 years. This is monitoring of the centrifuge production and the uranium production. Okay, but that's maybe getting too much into detail. Now, this is valid for 15 years, including shipping out, okay, I'll just say it, shipping out all the irradiated fuel away from Iran. So Iran can operate this reactor, but the irradiated fuel would have to be delivered out of Iran within less than a year from its irradiation. And this is for also 15 years. What about this PMD? So the agreement forbids any type of activity related to weaponization. Anything of this type is forbidden, even if there is an excuse for why it should be done for other purposes. Okay? So they are not allowed to develop detonators. They are not allowed to do calculations. They are not allowed to do hydro tests, of course, and so on and so forth. So in this sense, the agreement is very good. It prohibits all of these activities. But as we said before, our confidence that we will be able to identify such activity is not very high, and therefore we don't take it into account at all in these timeline estimates. Okay? Yeah. Questions about this? Yes.
How well do we know that they don't have other facilities, other centrifuges?
Yeah, that's a good question. It's always, yeah. So how do we know that there are things that we don't know? So the answer is that we don't. And so the main thing that we can rely on is that these are large facilities, okay? And intelligence services are quite efficient in identifying them. And the past experience of the Iranians has been that whenever they've tried to conceal such activities, they were caught, okay? So we cannot be absolutely sure. But the focus was on these type of activities for which we have a higher level of confidence compared to this type of activities for which we have lower level of confidence. Okay, so a few words about verification. The monitoring of this part of the agreement is under the responsibility of the IAEA. Now, the IAEA are experts on doing this type of job. Okay, this is what they do. This is what they know to do. The access to these facilities is very good. So it's a daily access, and also there are online monitors of the level of enrichment in the facilities that record the level of enrichment in real time. Okay, so we have good reasons to believe that this would be well monitored. Now, you might have heard some criticisms about the ability of the IAEA to monitor the program. All these criticisms were related to this part of the agreement, okay? Now, this is not the business of the IAEA. This is not what they want, what they know to do. So obviously there are gaps there, but as we said, this is not what the agreement is based upon. It will be the job of the intelligence services to catch these things if they happen. I would say one more thing, that even on these aspects, there are innovative steps taken in the agreement. For example, the IAEA can request access to any suspicious site, and which is not one of these declared sites, and the Iranians have to respond, and the process has to be concluded within 24 days. Okay? In the normal sort of challenge inspections carried by the IAEA in other places, there is no time limit. Okay? It can go forever. So there are innovations even there, some positive steps. Okay? But again, we do not rely on this. I would say one word about what happens when there's some dispute. Okay? So suppose that one of the states argues that Iran is breaking the agreement, or that the IAEA says that they are breaking the agreement. So this is dealt with by something called the Joint Commission. I will not go into the details of the process. The point is that they have about 30 days to reach a conclusion by which Iran should abide. The good thing is that this decision is by majority vote, and the commission is composed of the US, UK, France, Germany, the European Union, Iran, Russia, and China. So it's 5-3 to the West. So if the West decides that the agreement has been breached, this would be the conclusion of the Joint Commission. Now, once a conclusion of this type is reached, it goes up to the United Nations Security Council. And the United Nations Security Council has 30 days to make a decision to continue the lifting of the sanctions. So unless they reach a positive decision to continue the lifting of the sanctions go back automatically. And this is for 10 years of the agreement. Okay. Now maybe it's sort of time for a brief comment about the alternatives and what was really achieved. So overall, what was achieved in this agreement is 10 to 15 year time over which the Iranians would be hard-pressed to make progress on producing nuclear fissile materials. Okay? And we have some margin of 1 year to react if they decide to do something. In the end, whether or not this is going to be efficient depends on how resolved the powers are to take action in case they breach the agreement. Okay? If they breach the agreement and nothing is done, the agreement is not worth much. The alternatives, okay, some people have been discussing a military strike. So I will not go into any of these details, but you can read in the newspapers, analysis, and so on. I don't think anyone would argue that a military strike would buy you 10 years. Moreover, it would come with some quite negative consequences. And in the long run, I think our real hope is that Iran would make a decision at some point not to pursue this program. So in 10 years from now, Iran would have to make another decision. We've seen the decision that they've made now. Under economic pressure, they have decided not to pursue this program. I don't know what they will decide in 10 years from now. And we have to be ready for this development. Okay, so the intelligence, everything has to be ready for what happens in 10 years, but at least it gives some hope that there's some possibility that they would not make a decision to continue. A military strike would probably, not necessarily, but likely ensure that they would go in this bad direction. So even my prime minister, in his speech to your Congress, said that the alternative to the deal is a better deal, which is correct. Yes, just I'll complete the sentence. And now the issue of a better deal, it's of course good to press for a better deal. So I don't know, extend it to 20 years or reduce even more the number of centuries, all these things. It's good, it's all positive. But we have to ask ourselves what was the risk associated with this type of decision. So we have to remember that the coalition of Russia, China, the West, was crucial in the economic pressure exerted on Iran. And one had to take into account at least the possibility that trying to push for a more stringent constraint would lead to a breakup of this coalition. It's not obvious. I don't know. No one knows what would have exactly happened. But one of the possible outcomes would have been that Iran would say that, okay, look, we have gone to a reasonable deal here, and you're not accepting it. We are pulling out. Russia and China had lots of motivations to support such a move. So this is at least a risk that one should have taken into account when weighing the alternatives. Yeah, so you had a question.
Well, it sounds very reassuring, but the verification is focused on the production within Iran.
Right.
What might be the alternatives for having supply from outside Iran?
Right. So this is again a good question. It is similar to Neta's question. These things are of course forbidden, okay? The agreement doesn't allow Iran to acquire, certainly not fissile material, but also technology from outside. And how are you going to monitor all this? So again, this is not something that the IEA would be very proficient in doing. This would be the job of the intelligence services that would have to keep their eyes open and ears and every other sensor that they have to make sure that this doesn't happen. But again, an agreement cannot really deal with this.
So what are the Iranians saying? What is their normal reason for keeping those things? Are they claiming it's all for peaceful energy purposes?
Yes, of course.
So they're continuing to say that sort of.
Right. So, okay, maybe I'll say another word about this PMD stuff. One of the negative, in my view, aspects of the agreement was that these PMD issues were not resolved. So in order to overcome this hurdle, it was decided that there would be some process. A process meaning the IAEA would send questions to Iran, Iran would answer, the IAEA would send another set of questions, they would answer, and then they would conclude. So the Iranians have kept to this process. And the final report of the IAEA on December 15 on these issues was that the Iranians have kept to the protocol of dealing with this. But the conclusion remains the same. It has not changed. So this somehow, somewhat undermines, I would say, the IAEA's ability to enforce. Yeah.
In the news, there's been a number of focuses on missile launches.
Right.
And yet some of that is forbidden in the deal, and I'm not just sure of the overlap of what's
Right.
forbidden and what's being done, and where does that fit?
Okay, good. So this agreement deals only with the nuclear aspects. There are sanctions on Iran related to two other types of activities, terrorism and missile development. So these are left in place, okay? They are not part of this deal. So if they launch missiles, they do some missile experiments, they are in violation of other things, not of this deal, and the sanctions related to those activities could be increased or extended. Yeah. Avi.
Success of these negotiations, do you know if there was any idea to do it for other countries with crazy leaders like North Korea, and maybe I can name a few others?
Few others? Okay. Let's talk about North Korea. So there are, I think, two major differences between this situation and the situation with North Korea. North Korea had a plutonium-producing nuclear reactor, I guess at around 5 kilograms per year, in 79. And they had a separation plant in the beginning of the 80s. The first time IAEA inspectors set foot in North Korea was 92. So, like, we are talking 10 years after they've achieved all these things that we are trying to prevent Iran from achieving. So this.
Just to understand, the
Yes. Yes, but this is well before the stage they had nuclear materials. That's a very different story. Maybe I didn't mention that all these things have already been implemented. So in January 16 this year, the IEA issued a detailed report verifying that all these steps have been implemented. They've done this, I think the Iranians have done it in a super speed. And I think no one believed that they would do it so fast, but all these things are already there. So the uranium was shipped to Russia, the centrifuges were removed, the infrastructure for the centrifuges was removed, which is even more important than the centrifuges and so on.
All this makes sense except for the fact that they were within a few weeks in 2013.
Right.
And if they're within a few weeks and they haven't agreed to anything, the inspectors have been kicked out. That's the part that doesn't make sense. Why didn't they just finish it or change their negotiating position completely?
So I think this is the point that maybe is encouraging, that in the face of very serious economic sanctions and lots of pressure within Iran, they decided to halt and go into the negotiations. And
Took 3 years to have any impact.
what?
I said the sanctions took years to have any significant impact on the economy.
Right, but this started in 2006. It took many years, yeah.
So you're under sanctions for 7 years, and you still decide not to finish a few more weeks.
No, but they haven't been in a few weeks from 2006. They've been gradually building up the program all the time during the sanctions, and they stopped at this point. They were not at 3 weeks before that.
I mean, just from a game theory standpoint, it doesn't make sense. It does make you wonder if that means there is another stockpile somewhere that they haven't declared, because that's the only way it makes sense that you would supposedly stop there and then go back to, taking your breakout period up by 2 orders of magnitude when, in a matter of weeks, another week's worth of sanctions aren't going to have any impact. So, when you've already suffered 3 years of them. So, that's the part to me that just, is their position believable? That's the part that, from a game theory standpoint, it doesn't seem to make sense. How does anybody analyze that?
Okay, so I would say two things about this. First, I would not even pretend to make an analysis of the Iranian way of thinking and why they made decisions. Second, the basic point of the agreement is that we don't care about this. We don't assume anything about the Iranian decisions. We only want to make sure that physically, if they decide to break out and do everything that they want to do, because I'm assuming nothing about my ability to analyze their decisions. But if they make a decision to break out, it would take them about a year. Now, for the other part of the question of, okay, how do we know that there are things that we don't know? This, we have to put a lot of emphasis on intelligence to make sure that we have nothing slipping through our fingers. So, Scott would probably take over now for the questions.
I think I'm sure there are a lot more questions, but time is getting on. There's a reception following in Fold Hull where you can have more discussion. I'd just like to thank Eli for an extremely clear and authoritative talk. I don't think I learned enough to build a bomb in my backyard, but I think maybe now I know enough to know if my neighbor's building one in his backyard. Thank you very much.